hopefully that's streaming okay. Okay, good morning. It is 10 o'clock in the morning. It is Saturday, so it is time for Physics with Keith. Before I forget, I need to let everyone know that next week, I'm afraid it won't be on the Saturday. I've been asked to help out with an Isaac Physics teacher symposium, which is all day on Saturday. Actually, it's Friday and Saturday, but I'm not doing the Friday. So it's all day on Saturday, and so it starts at 10:30. Because of that, I'm not convinced I'll be able to do the Physics with Keith in the morning and then the symposium straight after it. So I will be moving next week's session to the Sunday. So it will still happen, it'll just be one day later, and then after that we'll go back to being on the Saturdays again. I will put reminders on Facebook. But you know, sometimes these things happen. This is a live tutorial, a live tuition session, so if you want to ask any questions, then please don't hesitate to do so. The best way to do that is through the YouTube chat. I can see already that Freya's dropped a little message there saying good morning to you as well. If you want to send me a more private message because you don't want the announcement across the whole world of who you are, some people are funny about that sort of thing, then go ahead and stick it on Facebook Messenger, and I'll get the messages through to my phone, and I can then respond to anything there. So I'll leave my phone open in front of me as well. I've had two questions today, well, not really two questions, two topics today that a student wants me to go through, both at GCSE level. And one of them is the most fundamental idea in physics. It's so fundamental that that's what I'm going to start with. And it's one of the areas where students most often make mistakes that will cause them to have so many problems in the future of their physics education. In fact, the majority of people get it wrong. This is, in the entire world, most people get this wrong, and it causes us lots and lots of problems. I am referring to Newton's 3 laws of motion. So I'm going to start by talking about Newton's laws of motion. They're not that scary. They're really not too difficult either. The problem is that you have been exposed to incorrect interpretations of Newton's 3 laws of motion for your entire life. And so because of that, it's generated these misconceptions in your mind that you're clinging to quite strongly, and we need to fix that. We need to break those misconceptions that everyone has and make it so that you have a far stronger understanding of physics. And once the penny drops, once it clicks into place with Newton's 3 laws, the rest of physics really just flow from it afterwards. Physics is just forces and energy. That's all it is. So once we got the forces bit sorted, that's half the battle won. The other topic that I've been asked to go over is density. And I've got some questions that I can ask about density, and the trickiest part of density questions is often the conversion of a volume into some more sensible units. So we'll talk a little bit about density as well today. I can see that I've got 3 concurrent viewers according to YouTube, although I believe one of those is me, so that's 2 concurrent viewers. That's wonderful, and one of you has already made yourself known to me. But, and I've got a little message come through on the Facebook Messenger from somebody else as well. So I guess that's the 2 people that are viewing. Hello and good morning to you. So let us start with Newton's 3 laws of motion. As I say, the most fundamental idea in all of physics. They can be summarized quite quickly, but then we need to go into the implications of them to get a better understanding of what they mean. So the first of Newton's 3 laws of motion can be summarized in one word: inertia. Inertia is the idea that things in the universe do not change their motion spontaneously, and we'll go into more detail about that later. The second of the 3 laws can be summarized with an equation, but it might not be the equation you're expecting. It's this one. Okay, force is proportional to rate of change of momentum. We'll have to talk about what that means and what is this force in a little bit of detail. And the third one is the one that causes so many problems. You may have heard of it as every action has an equal and opposite reaction, but that is the worst possible wording that you can learn for this. The problem is that wording is so ubiquitous, which means that so many people use it, it's entered the common understanding of everyone. And because of that, and because of that badly worded description of Newton's third law, people really don't get it. So I find a better wording is that forces come in pairs. And there are 5 conditions, 5 properties that those pairs of forces share. So forces come in pairs. Let's have a look at the first of those laws, so inertia. And I want you to consider a ball. A ball, I'm not a sports person, so maybe this is a tennis ball, maybe this is a golf ball. It's some sort of ball that has been projected, it's been launched, it's been struck in some way, maybe with a tennis stick, maybe with a golf stick, maybe with a cricket stick. There's a lot of sports that involve sticks and balls. And this ball is moving through the air. And let's say it's moving in this direction through the air. Flying through the air in this direction. What I'm interested in is what forces are acting on that ball. Now, I'm going to give you a few moments. If you want to drop your thoughts down, what forces do you think are acting on that ball? It's in the air, it's mid-flight, maybe it's at the highest point in its mid-flight. What forces do you think are acting on that ball? Just list as many as you can think of. So Freya said gravity. It's good, let's add that one. Are there any more? Let's add gravity and then I'll let you think, are there any more? So I'm going to label gravity in blue today. And I'm going to label gravity, I'm going to label it weight instead of gravity. Gravity's fine, especially at GCSE level, that's fine. The word gravity at A level is a little bit too vague, so if you're an A level student watching this, it's not okay at A level, but GCSE level gravity's fine. I'm going to label it as weight. Air resistance has been said, and friction has been said. Well, I suppose air resistance is a frictional force, so absolutely yes, there will be some air resistance, and I hope you would realise that that air resistance is in this direction. If we are moving from left to right, then there'll be a bit of air resistance acting from right to left. It's not going to be very much though, but I'll label that. And in fact, just to be difficult, I've had 2 messages come through, one saying friction, one saying air resistance. I'm going to go ahead and label that drag. Sometimes it's called viscous drag, sometimes it's called fluid drag, so I'm just going to call it drag. Any more forces acting on that ball? Okay, so a message just come through saying potential energy. But potential energy isn't a force. It's a store of energy. Potential energy doesn't have a direction associated with it. Any other forces acting on this body, which is at the highest point in its journey? It's got the weight acting down, drag pushing to the left. Any other forces? If you can't think of any other forces, then just say no, I don't think there are any other forces. But if you think there is, even if you're not quite sure what it's called, maybe describe it. So on the Facebook Messenger, we've had push force has been mentioned. Push force. Well, I like your answer, but it's not quite right. It would be true if I was still touching this ball and pushing it. So let's imagine I'm playing the tennis game, and this is a tennis ball, and my bat is still in contact with the ball, and I'm still pushing it, then yeah, sure, that would have a push force. But in this case, the ball is not in contact with the bat. So I'm not actually pushing it. The ball left the bat some time ago. So there's no push force to the right. No. No other messages coming through. So I'll put you out of any potential misery you may have. There are no other forces acting. And there's one more, there is one more, but it's absolutely tiny. There's a diddy little force called buoyancy, which acts up. But when I say diddy, it's between a tenth of a percent and 1% of the weight for a spherical body. I'd have to work it out. But it's tiny, tiny little bit of buoyancy force just because this ball happens to be in the air and it's displaced the air. So the weight of the air that's been displaced is producing this upward force on this ball. It's the Archimedes principle. But I cannot emphasize how small that force is. And at GCSE level and at A level, we assume that buoyancy is negligible, that it is zero. In fact, even in the most advanced parts of A level physics, which is the Millikan experiment, measuring the charge of an electron with the Millikan experiment, even there we assume buoyancy is negligible, that it is zero. It's such a small force. And that's it. Now, you see, the body is still moving to the right, but there's no force acting to the right. There is no force acting to the right at all. And if we were in a vacuum, so there was no air, there's no fluid through which this ball is moving, there'd be no drag force. So in a vacuum, maybe we're on the surface of the moon and we've just struck this ball. I understand that that is something that the 6 astronauts that have walked on the moon, 12 astronauts that have walked on the moon did. 12 astronauts have walked on the moon. And I understand that they played, some of them played golf and hit a golf ball and it moved through the air like this. And there's no air, there's no fluid through which the ball is moving. So there was only one force acting on it. But that still moved forward despite the lack of a force. You think, well, why is that? The answer is you don't need a force for things to be moving. You need a force to change something's motion. You can have things moving quite happily without there being a force, as long as they were already moving. Consider, for example, the moon. Doesn't have jetpacks or boosters firing to make it go around the Earth. It just keeps moving because it started moving. There's no reason for it to stop spontaneously. The Earth going around the sun is the same thing. If you don't believe in this idea, take a bicycle, go to an ice rink, get somebody to push you from the edge so you're moving, and then hit your brakes and you're not going to stop. You're going to keep moving. Don't do that, by the way. That's incredibly dangerous and it would really, really hurt. But as a thought experiment, it does the job. It tells us you don't need a force for there to be motion. You need a force to change motion. And that's Newton's first law. A better way of wording it would be that the velocity of a body, which is its speed and the direction in which it's moving, the velocity of the body is constant if the resultant force on the body is zero. Resultant force is the force you get when you add forces together. And I can't remember if I've done a session on vectors or not. If I have, then let me know. If I haven't, then also let me know, and I can do a brief summary of vectors. But when you add up the effect of all of the forces on the body, if that effect is zero, or the forces cancel out, then the velocity of the body isn't changing. Okay, so that's Newton's first law covered. Oopsie. Any questions about Newton's first law? Please do ask. If not, I'll move straight on to Newton's second law. Newton's second law, we have this equation here. Force is proportional to, and then we've got this delta P over delta T. Now, delta P is the change in momentum, also called impulse of a body. And impulse is it's a nice fancy term, which means change in momentum, which is the mass of the body multiplied by the change in velocity of the body, or actually technically the change in mass times velocity of a body. So we could rewrite Newton's second law as, if the constant of proportionality is 1, which we take it to be 1, so that's why we use the unit called the Newton in honour of Isaac Newton, we write down this equals ma when our mass is constant. Because when our mass is constant, m times a is equal to m times v, change in v, should I say, delta v divided by delta t, delta v over delta t being acceleration, and m delta v for constant mass is delta p. So there's the same equation. Oh, I've gone under my head there a little bit, so I'll just scroll. There we go. Right, now you don't always have constant mass, so A-level physics students will be aware of the weak nuclear force and how that changes momentum by changing mass and exciting things like that. But for everything in GCSE level physics, the equation F equals ma is a pretty good approximation of Newton's second law. It's a pretty good example of Newton's second law. It works for constant mass. The fly in the ointment with the second law is that F is the resultant force and A is the resultant acceleration. And so if I have two forces acting on a body, I have to find the resultant force to find what the acceleration of the body is. It's not possible for a body to accelerate in two different directions. It's one body, it's going to have one acceleration. But one body can have more than one force acting on it. So we have to find the resultant force on a body in order to find what the acceleration of that body is. So again, if I did do a session on vectors and finding resultant vectors, that's good. I can't remember if I did. If I haven't and you want me to go through it, just drop a comment saying, yes, just talk me through resultant vectors, please, and I can quite quickly do that. But otherwise, that's Newton's second law done. Nice and simple. Some implications of Newton's second law. If you want a force of a collision, for example, to reduce, what can you do? So if I want a smaller force of my collision, let's get my little handout here. Let's say it's a car driving along and it crashes and I want the force on the car to be as low as possible. I can either have a lower momentum, which means make sure the car's going slower. We know that's true. If the car's moving slower, the collision has less force. That's why it causes less damage. Or we can make the collision take a longer time. If the denominator is larger, then this fraction is smaller. That's how fractions work. So a bigger collision time reduces the force, the resultant force, on a body. That's what crumple zones do in cars. When you have a crash, the crumple zone is designed to increase the time of that collision, the duration of that collision, so that the force, the impact force on the car, and therefore the people inside the car, is lower. So that's Newton's second law. Right, let's do Newton's third law. This is my favourite one. It's so good I wrote a song about it, which I won't sing to you now, but if you look on YouTube for Newton's Laws Blues, you'll find it. The chorus is just Newton's third law over and over again. Newton's third law. There are 5 conditions that pairs of forces share or have. But before I go into that, it is the most common mistake. It is the most common problem. So having said that, I'm about to ask you some questions where you know you're about to get things wrong. Okay, the nature of this, I've told you this is very often something that students get wrong. I'm about to ask you questions. You know you're going to get the answers wrong, so don't be afraid to answer in case you get it wrong, because you're going to get this wrong, so let yourself get this wrong. That's how you learn. If you look on this little simulation, I've got a car. This is a simulation by John Nunn, Dr. John Nunn at the National Physical Laboratory. He very kindly has given me permission to use these in these live tutorials as long as I give him credit for it, which is what I've done. If you go to the National Physical Laboratory website and search for Virtual Physics Lab, you can find these simulations. So in this car, I'm going to accelerate and I'm going to have a look at the forces acting on this car. So let's get this thing accelerated, get it nice and fast, and we'll look at the forces acting on the car. I'll tell you what, I'm going to move the position of the engine to the middle, so these forces are all a bit easier to balance. Okay, so Newton's third law, forces come in pairs. Let's see the mistakes that we're all going to make, and you're definitely going to make them. And you can refer to the forces by colour here. So, the red force. What's the paired force to the red force? Forces come in pairs. There's the red force, whatever that force happens to be. You can refer to the force by the force's colour on this diagram, or you can refer to it in some other way, maybe the name of the force. What is the paired force to that red force? Drop your comment in, let me know what you're thinking. Okay, so I've had the answer friction come through from the Facebook, which I suppose technically is true, but which friction arrow? Where is the friction acting? Maybe give me a little bit more detail. Where is the friction acting, this friction force? Bear in mind, if you get this right, you're actually the first person in my history of teaching, which is more than a decade now, who has got this right. Friction on the wheels. Friction on the wheels would be incorrect. Not a friction on the wheels force that's paired. So the red arrow is the friction on the wheels. That's what it is. That's the road pushing the wheels forward because of friction. That's what that red arrow is. A thrust from the engine, but we're not going to call it thrust because it's not a thruster. It's not technically a thrust. The push force, but push is a little bit too macroscopic for this, so we could call that the floor pushing the wheels forward because of the force of friction. So that's the red arrow is on the wheels. So what's the paired force to the red arrow? Freya's been quiet for a little while. Hopefully she's now having computer problems. Thinking, good, good. Allow yourself to get it wrong. You learn from your mistakes. Allow yourself to get this wrong. No judgment from me. You're not sure, and that's okay. It's okay not to be sure. I imagine that you're looking at this and thinking, well, I know it's not the blue arrow because he's told me that it's not the obvious one. He's told me I'm going to get it wrong. So I'll ask you a slightly different question then. In fact, I'm going to get rid of this simulation. Let's draw a slightly different question. Drag, which is the blue arrow. I'm afraid not. It's not that blue arrow. So let me ask you a slightly different question. I'm going to do my best at drawing a sketch here. Wish me luck. Here's a chair. A quality chair. There we go. Some teachers can do really good diagrams. Some teachers, like me, cannot. Okay, so here's a chair. And let's have somebody sitting on this chair. Here's the person sitting on this chair. Like this. Minding their own business. The person has two forces acting on them. Let's draw a force downwards in purple. Let's call that the weight. What's the paired force to that one? Don't be afraid to get it wrong. What's the paired force to this one? The person feels a force down. It's their weight. We all learn that forces come in pairs, or you learn this awful, horrible alternative wording. It's not resultant. Resultant is what we call two forces when added together, the force that is produced by those two effects. That's what we call a resultant force. So to give you an example, if I had a hovercraft, let's draw a quick sketch in this big pen. Here's a hovercraft. If the hovercraft engines are pushing it forward but the wind is pushing it sideways, the resultant force is up here. Oh, let's move my things gone under my head. The resultant force is up there. It's those two effects added together. So that's what we mean by resultant. What's the paired force? Static force has been written here. I wonder what you mean by static force. The word static usually means not moving. And not moving, well, yes, this person isn't moving, but there's not really a force called static. I wonder whether you're referring to the force that's produced by charges, because we've heard of the idea of static electricity. And we'll talk about the force produced by two charges. Maybe you're talking about the contact force between the person's bottom and the chair, pushing up on the person or something like that. Freya said uplift. So the person feeling that force up. Uplift isn't really a force, but maybe you're thinking of upthrust, which is another name for buoyancy. Remember I said that buoyant force is here, but it's absolutely tiny, so we're going to ignore it, and that's not the pair to this force. No, this is a weight acting down. So where's the paired force? Okay, I'm going to tell you the formula to figure out what the paired force is, and you will know it forever. This is the force that prevents falling through the ground, has been said on Facebook. So that's a sort of a contact force between the person in the chair, preventing the person falling through the ground. Resistance, the idea of that. So you're all describing basically a push force upwards on the person. Is that fair to say? You're all thinking to yourself, and you're trying to get the right words for it, but you're all thinking to yourself of a push force upwards on this person, right? Because that's where we've gone wrong. It's not a push force on this person. So here's the formula to figure out Newton's third law. Learn it and you'll know it forever. Switch the nouns, switch the direction. Here's what I mean. That purple arrow is the person attracted because of gravity down towards the earth. So person attracted because of gravity towards the earth. So down. The earth, so we switch the nouns, person and earth. The earth is attracted up towards the person because of gravity. Switch the nouns, switch the direction. The earth is attracted up towards the person is attracted down towards the earth. You switch the nouns and switch the direction. I'll give you a slightly different example and then I'll show you the 5 conditions. So here's another example. Here is a big box, and here is a person who wishes to push the big box. Here's the person, and they push on this big box. Newton's third law says that the person pushes the box to the right. The box pushes the person to the left. I'll switch the directions. I've switched the nouns. Forces between two bodies always come in pairs. And the two bodies in this picture are the person and the box. Person pushes the box to the right. Box pushes the person to the left. How many forces are on that box right now that I've drawn? 1. And it's to the right. How many forces are on that person that I've drawn there? 1. And it's to the left. The two forces are on different bodies. So here we go. You will not find this in textbooks, what I'm about to tell you, because, well, I've never seen it in a textbook. You will not find it in GCSE physics notes anywhere unless you happen to have been taught by me. These are the 5 points. I can't remember where I heard them, but they've stuck with me and they will help you. Point number 1. If you have a Newtonian pair of forces, they are always the same magnitude. The same size, the same amount of newtons. If I push a box with 10 newtons away from me, the box pushes me backwards with 10 newtons as well. The second point, this is point number 1, or A. The second point, why have I put a 2 there? It was Newton's third law. Let's change that to a 3. There we are. So the second point, the two forces have opposite direction. So far, this sounds a lot like that horrible wording, equal and opposite. We don't like that. My problem is equal and opposite for vectors is nonsense. You cannot have two vectors that are equal and opposite. If two vectors are equal, they have to have the same direction as well as magnitude. So you cannot possibly have two vectors equal and opposite. Those two statements are mutually incompatible. So two vectors of the same magnitude in opposite direction, and here's the part where we fix those misconceptions. They act on two different bodies. So act on different bodies. If you have two forces acting on the same body, they are not a Newtonian pair. They may very well have the same magnitude and be in opposite directions, but that does not mean they are the pair of forces. Each of those forces has another force paired with them. And now for the last two that are going to change everything. Number D. They act in the same line of action. Same line of action. What I mean by that is the forces, if I drew an imaginary line through the universe that went past through the position, the point where the force is acting, and went in the direction of the force, somewhere along that line would be the paired force, and it would act in exactly the opposite direction, that's point number B, but along that line. They're along the same line of action. If you imagine the person sitting on the chair, it's entirely possible the person can rock back on their chair. If they rock back on their chair, their weight is acting down, the push force from the chair is acting up, but they're not necessarily in the same place. The person in the same line of action, the person can rotate and topple off their chair. That's entirely possible. The fact that people can topple off their chair means that those two forces are not in the same line of action, but also it says act on different bodies. The chair pushing the person up and the person being attracted down, those two forces are both acting on the person. So they're not acting on different bodies. So although they have opposite directions in the same magnitude, they do not satisfy point number C or point number D. And the last one, and this is the easy check, they're the same type of force. A push force is paired with a push force. A gravitational attraction is paired with a gravitational attraction. An electrostatic repulsion is paired with an electrostatic repulsion. A friction force is paired with a friction force. So, let's have a look at our car. That red arrow is acting on the wheel. All of these forces I've drawn here are acting on the car somehow. They are all forces on the car. So none of those arrows is paired with any of the other arrows drawn on this picture. So if we want to draw the pairs, we need to make the picture bigger. So here's my picture. Now I'm going to have the flexibility to doodle on it. So let's start with that red arrow. In fact, let's make this slightly bigger so you can see it more. Let's scroll across to the right. That'll do. Right, so we've got this red arrow. The ground pushes the wheel to the right. That's sort of what's pushing the car along, isn't it? The ground pushes the wheel to the right. Switch the directions and switch the nouns. Type your answer. What's the paired force to this red arrow? This red arrow is the one I'm trying to highlight it. It's not actually highlighting on the picture. Brilliant. This red arrow is the one I will circle in yellow here, in case anyone's watching this and has some colour blindness and doesn't know what the red arrow is. It's possible. That's the red arrow. So type the paired force now. The ground pushes the wheel to the right because of friction. So now switch those nouns and switch those directions to get the correct answer. What's the paired force to that red arrow? The ground pushes the wheel to the right because of friction. The wheel pushing the ground to the left Perfect. Well done, Freya. Absolutely perfect. The paired force to that red arrow is in the same line of action. The ground is being pushed to the left. That red arrow I've just drawn is on the ground, not the car. It's the same length because it's the same magnitude force. It's in exactly the opposite direction. They're on the same line of action, and they're the same type of force, a friction force. And I think I've said everything now. And they're on two different bodies. If you don't believe me, take a car on the beach and then rev your engine and get your wheels spinning. The sand is pushed back by the wheel, and the wheel is pushed forward by the sand. And actually, because the sand has such small mass, each individual grain of sand, Newton's second law, F equals ma, small mass sand has big acceleration for a certain force. So the sand gets thrown out the back very, very quickly on the car. The car doesn't go very far because of the tremendous amount of drag that you've got through that sand, which acts a bit like a fluid on the other wheels, but we're not going to get into that at the moment. So, let's look at next. These green arrows. The ground pushes the wheel up. What's the paired force to those green arrows? The ground pushes the wheel up. Write your answers. Teddy, if you want to write your answer as well. Not gravity, no. No, remember, just switch the nouns. The two nouns are wheel and ground. Freya's got it. Okay, the ground pushes the wheel up, so the wheel pushes the ground down. Okay, the equal force is on the ground. It's in the same line of action. It's going down, the same magnitude. The ground is pushed down. And if you don't believe me, then take a car onto some quicksand. Take a car onto some quicksand. The sand will be compressed, because it feels that force pushing the sand down. The sand feels that force down, and the sand pushes the wheels up. Perfect. We've got the next one, the blue arrow. The blue arrow is the air pushing the car to the left. So what's the paired force to that blue arrow, which is acting on the car? The air pushes the car to the left. So what's the paired force? Remember, Teddy, just switch the nouns and switch the directions. The air pushes the car to the left. Freya's got it. Teddy's still not quite there yet. You have to give it as a full sentence. Full sentence. If the air pushes the car to the left, the paired force is the, as Freya says, car pushing the air to the right. So the car is pushing the air to the right, like this. Perfect, right? Teddy's got it. Perfect. And if you don't believe me, when you're driving down the road and it's snowing, have a look what the snowflakes do as they approach your car. They don't actually hit your car. Because the air is being pushed forward away from your car, the snowflakes sort of flick away from the windscreen before they ever hit it. You don't have to believe me. You can drive down the road in the snow and just sit and look through the window and look. You see that happening. And so the last arrow is the earth attracting the car down. And this is a gravitational attraction. The earth attracting the car down. Where's the paired force to that one? The earth attracting the car down. Okay, so Freya's got it. The car attracting the earth up. Teddy's written the car attracting the ground up. Definitely talk about the earth rather than the ground. What we're talking about here is the entire mass of the earth is attracting that car, and the car is attracting the entire mass of the earth. So the force arrow that I would draw I'd have to scroll down quite a long way here because I would draw it acting on the centre of gravity of the earth. which is going to be the centre of the Earth. And the length of the arrow will be the same length. I'm not able to draw it on this diagram because I made the car picture too big. But it will be on the centre of the Earth, same length arrow upwards. Now let me ask you a question to try to convince you that this is true. When you jump, what do you do? It's a very simple question. When you jump, what do you do? Nice open question that you're going to struggle to answer. Think about the mechanism of jumping. Maybe you're playing a game where you have a ball that you have to put in a hoop. That's a game people play sometimes. When you jump, what do you do? You leave the earth upwards. Absolutely, that is what you do. But I'll tell you what you don't do, Freya. You don't push yourself up. When you jump, you do not push yourself up. You can't push yourself up. You cannot push yourself. You can't do it. You cannot push yourself up. What you do is push the ground down. That's what your legs are doing. When you push with your leg muscles, you're pushing the ground down. So what's the ground doing? There it is, pushing you back up. Let's ask you another question. There's a rope, you want to pull yourself up on this rope. You can't actually pull yourself up, can you? You cannot pull yourself up. You cannot push and make a force on yourself. So if you want to climb that rope, what do you do? So Teddy said, with the jumping example, push earth down. Yes, you would push the earth down. The earth would push you up, so it's the same type of force. And then with the rope one, he's got it right. You pull the rope down, so the rope pulls you up. Okay, keep the force the same type. If you pull the rope down, the rope pulls you up. If you push the earth down, the earth pushes you up. All you switch is the nouns, and all you switch is the direction. And if you do that, you'll be fine. Difficult concept. But let me tell you why the misconception is absolutely false. The idea that on one body forces are paired. I'm going to show you now the mistake students make. And this is, you know, in terms of education, dangerous, because there's the risk that students will see the mistake and then that's what they'll remember. So this is absolutely, when I teach this in school, sometimes I do something here which is perhaps a little bit unprofessional. I put a special hat on. I wear the hat, so it's not like I make other people wear it. That would be awful. A special hat. And I say, I'm going to put this special hat on. Whenever I've got the hat on, it means that whatever I'm saying is wrong. And I put the wrong hat on. And everyone that sees me then goes, okay, he's wearing the wrong hat. That's not what I have to remember. It does work. So here's the person sitting on the chair. Here's the mistake that people make. They draw the person sitting on the chair and they think, okay, well, I've got the person's weight acting down, and then every action has an equal opposite reaction. So weight goes down, chair pushes person up. And they go, there we are, that's the pair of forces. Obviously that's not true. Because if it were true that on a body there were always equal and opposite forces, then think back to Newton's first law, inertia. If on a body there's no resultant force, its motion will never change. And so if forces acting on a single body are always equal and opposite, nothing can ever happen. There can never be acceleration. Newton's second law, resultant force, if for a constant mass, resultant force is directly proportional to acceleration. Nothing can ever accelerate and therefore change motion if there isn't an unbalanced force. So we know, experience tells us that there are unbalanced forces. But now I'm telling you that forces also always come in pairs. And that pair of forces is on two different bodies. And once you've cracked that, once the penny drops, once you've mastered that, the hardest part of physics has been done. How are you feeling about that topic? Nice vague question for you. You've done a few examples now. Freya, you've had several correct answers in a row. Teddy, you've got a few correct answers in a row. I think you two are still the only two people that are watching this. So, no. So Freya's saying that was good. Thanks. Hopefully you've cracked that now. I know you said you wanted me to talk about density, so I will quickly talk about density as well. Teddy, feeling pretty confident about that? Good, yeah, super. Honestly, this is, so many people get this wrong. TV gets it wrong, cartoons get it wrong, older siblings get it wrong, parents get it wrong. I'm going to tell you a horror story now. When I was training to teach, I was in a department, one of the schools I was teaching in, I won't name the school, that would be awful. One of the schools I was teaching in, I was the only physicist in the department. And they asked an expert from the Institute of Physics to come in to help them with their teaching. And one of the first things he did was draw a ball, just like I did here, and ask the teachers, to draw the forces acting on it. And every single one of them drew a force forward and said, well, there must be a push force. And then every single one of them drew a force up, opposite the weight, and said, well, there must be a force there because of Newton's third law. And they're teachers. They were teaching GCSE students at science and in physics to take their exam, and they got it wrong, every single one of them. I was gobsmacked. And they were good teachers. They were absolutely brilliant at chemistry, at biology, but they weren't physicists. And this misunderstanding is so prevalent. You can understand why they would have it. So be warned. Okay, let's move on to density. That was a good 45 minutes of me rambling on. I like rambling on about Newton's law. It's one of my favourite topics. So glad somebody asked me about it. Okay, density. Little bit simpler now. Density, we're going to use the Greek letter rho, not to be confused with the letter P. Letter P, we start from the top left when we draw it, like that. So I'll just get my cursor out so you can see what I'm talking about. When you draw a P, you start from the top left, go down, back up, and then curve around. That's the normal way of drawing a P. With a rho, I'm not an expert in writing in Greek. You can either start from here and curl it around like this. A colleague of mine prefers it that way. I prefer to start at the bottom left and curl up, just because it's much clearer that that's not a P. If you think, does it matter? It does, because in physics you're going to meet equations that have P and rho in the same equation. So if they look the same, you're going to struggle. So make sure your rho looks different. My colleague, by the way, starts from the middle and draws his rho curving around a bit more like that. I'm worried about that because it looks too similar to the letter E. Although, if you think you're drawing it on a line, then it's more obvious it's not an E, but I don't know. I get nervous about that sort of rho. I prefer this sort of rho. Anyway, that's by the by. Practicing the Greek handwriting, rho equals the mass of a body divided by the body's volume. That's all. Rearranging this equation, very straightforward. So if we want to get the mass as the subject, we multiply both sides of our equation by volume to get rho v. And if we want to get the volume of the body, then we multiply both sides by volume and divide both sides by density to get volume equals mass divided by density. I will never promote the use of formula triangles. I have a poster in every physics lab in my department banning formula triangles. I know there are teachers, including teachers in my school, that quite like the formula triangles, but none of them are physicists. Because when you get equations like this further down the line, let's give you an example. Gamma 1 over the square root of 1 minus v squared over c squared. Nice equation like that, which you derive in year 13. Formula triangles aren't going to help you. And as a physicist, I'm training students, young people, to understand physics, and you can't do that if you're drawing sort of triangles and sneezing 3 values into that triangle and hoping that when you cover one up it gives you the right answer. No. Any resource document, any revision guide that tries to use these triangles is dumbing it down in a way that is detrimental to your future. So I'm afraid I'm never going to promote them. I've heard arguments in favour of them, people saying, oh yeah, but it helps them get through that initial stage, or well, it's just a tool to help you learn to rearrange equations. I really don't think it's a good tool. I think it's far better to just do the same thing to both sides, because that's the rule that you use right the way to the end of your degree in physics and beyond. Just do the same thing to both sides, and it starts practicing at this level. Not using formula. Okay, I've ranted again. So no formula triangles. These are our equations. So what's the problem? We're just plugging numbers in. So if I said to you, I've got a body of mass equal to, oh, I don't know, 10 kilograms, and a volume equal to, oh, I don't know, 20 cubic meters. What's the density? Why don't you go ahead and write your answer? Try to pick numbers so you wouldn't necessarily need a calculator. So 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. That was the 7 Mississippi latency caused by streaming. You may be getting a calculator out. If you are, you really don't need to. 10 divided by 20. Okay, so we're after a density, so the answer would be 0.5. That's the number part of it. Now let's look at the unit. Okay, I'm going to tell you something here that if you've never seen it before, this is going to change your life. You're going to love it. You never have to remember a unit again. Let's write the numbers with the units in our equation. So instead of m, I'm going to write 10 kilograms. Instead of v, I'm going to write 20 meters cubed. So put units in your equation. The answer, so 10 divided by 20 is indeed 0.5. Kilograms divided by meters cubed is kilograms divided by meters cubed. That's the unit. You can use units in equations. And what's nice about this is if you're in an exam and they give you a density and ask you to find a volume and you can't remember the equation, the unit tells you the equation. It's wonderful. You don't have to remember the equation if you've got the unit, and you don't have to remember the unit if you've got the equation. Very, very powerful. It works for speed, distance divided by time, meters per second. It works for, well, it works for anything. So, what's the problem then? The problem is volume. That's often the problem. So if I tell you I've got a liquid, I've got, it's really helpful. No one ever showed me that when I was at school, and I wish they had, Freya, because just the fact that you can put units into equations is amazing. But here's the problem. Let's say I've got a liquid. It's not water. It's not water. And I've got maybe 12 grams of this liquid, and it is occupying 10 cubic centimeters. So this is the mass of the liquid. This is the volume of the liquid. And you'll say, what's the density? The density is 12 grams divided by 10 cubic centimeters, which is 1.2 grams per cubic centimeter. Oopsie, cm cubed. That does say cm. Oh, by the way, in exams, never do that. If you make a mistake, draw a line through it and write next to it. Never just scribble over your answer, because the examiner, if they can't see it clearly, they cannot give you the mark for it. There we go. So that's fine. What if they'd given you millilitres? Some people like a capital L for litres. Some people like a lowercase l for litres. What's the density now? Now you're going to say 1.2 grams per milliliter. Yeah, but I want the density in grams per cubic centimetre. Difficult. So it's not that difficult. There's a little bit of information you need to know that you're not told, that you should remember, which is 1 cubic centimetre is 1 milliliter. So actually it's exactly the same density. Super. So what if they give you some different numbers? What if they give you this? They say I've got a lot of liquid. Maybe I've got 10 kilograms of this liquid, or whatever it is. I'm just picking up numbers here, so it might not make a lot of physical sense. And I've got 10 litres of it. Alright, that doesn't make any physical sense at all. Okay, so 10 litres of whatever this substance is, which is 12 kilograms, what's the density now? And I want the answer in kilograms per cubic metre. Oh dear. Much more difficult to solve. So to solve this, we are going to use this here. And step 1 is going to be to convert the volume into cubic meters. So let's do the volume conversion first. And work along with me as you go through this. 10 litres. I need to get this into units something to do with cubic meters. So I'm going to multiply this by the number 1. Now, okay, that sounds stupid, so I am going to scrub that out in a minute and give you a better answer. But do you agree that if I multiply something by the number 1, I don't change it? Hopefully you're all just typing the word yes. Yes, absolutely, yes. Now, do you agree that if something is equal to something else, so let's say A equals B, then A divided by B equals 1. Something divided by itself equals 1. Let's move those over here. And so hopefully you're thinking to yourself, yes, I've got that. I agree with that. If I divide something by itself, it equals 1. Yes. And what we've got over here is 1 cubic centimetre is 1 milliliter. So I can divide this by 1 milliliter, 1 cubic centimetre. And multiply it by that. All I've done is multiply it by the number 1. Why have I done that? Because that allows me to cancel the litres. And I'm left with just cubic centimetres. Careful, because I've got a milli here, which I'm going to have to deal with in a second. But I can cancel the units, litres. Okay. So what is that milli? Milli is equivalent to times 10 to the negative 3. That's what millilitres is. Times 10 to the negative 3 litres. Now, I know that... Oh, Teddy's got an answer. We'll see if you're right in a second. Freya, I know Teddy probably hasn't met this notation before, but Freya, have you met this notation? Times 10 to the negative 3, meaning milli. Or a thousandth equaling milli. Yes, good, okay. So, yeah, whenever you see the milli, go straight ahead. The problem is here, at the top of the fraction, because we've got this thing called centi. So if we want to convert centimetres cubed into metres cubed, I'm going to want centimetres cubed on the bottom, metres cubed on the top. This is the easiest way of thinking about it. You would be forgiven for thinking it was this. It's not. The centi part is also cubed. And so it's not 100, 100 little centimetres is 1 metre, but 100 times 100 centimetres is 1 metre squared. And 100 times 100 times 100 centimetres is 1 cubic metre. So it is not 100, it's 100 to the power of 3. The centi part is cubed as well. And that allows you to cancel the centimetres cubed, and you're left with that. Now this is quite tricky, and I'm trying to cram all this into the last few minutes, so maybe we can look at this a bit more next week. Might be worth us looking at this again next week. But if you work through the maths now, what you've got left is 10 multiplied by 1 over 10 times 10 to the negative 3, 1 times 10 to the negative 3, multiplied by 1 over 100 cubed, equals, and that's going to be our volume in cubic meters. I mean, you can do this in your head, but I'm going to see if I can make a mistake on my calculator. So 1e3 minus divide, and 100, enter 3 power, and divide. Okay, so you get a volume of about 0.01 cubic meters. Okay, that's what 10 litres is. And then if you use that in the equation above, so density is going to be mass divided by volume. We can now plug in our 12 kilograms. We can now plug in our volume now, which is in the unit we want it to be in. And we're left with 1200 kilogram per meter cubed, which is what we were after. Okay, that is difficult. Converting volumes is difficult. I have got a drill which I made. I think I've told you about my drills before. Let's just go to Physics with Keith, Electronic Resources, scroll down to Volume Drill, Length Area Volume Drill. Here we are. So I have got a drill which I think I may have shown you before. If not, I'm showing you now, which is so it's basically question after question after question of convert this length to that length, or this volume to that volume, or this area to that area, and if we click answers, it gives you the answers. And if you want another set of questions, you press F9, it changes all the numbers, changes all the units. You just keep pressing F9, you keep getting different questions. It's worth using something like that to practice converting these lengths, volumes and areas until you're fluent in it, until you don't make mistakes with it, because it is a common problem that students come up against. If you want a copy of that, let me know. I'll get it sent to you. Very happy to do that. Otherwise, it's 11 o'clock. We've been at this for over an hour. I think it's time to stop. If you could, sorry, I will remind you, that next week I'm not on Saturday because I'm doing a teacher symposium for Isaac Physics. So if you tune in on Sunday, I will put reminders on Facebook, but if you tune in on Sunday next week, then we can pick this up. And if you want to do some more unit conversion stuff next week, it's worth looking at. Do just drop me a message and let me know. The other thing I want you to think about is I've been pondering the possibility of doing a some sort of a summer catch-up course online for GCSE. Again, it would be free. This isn't something I'd be charging for, but I'm not really sure how to go about it, how many sessions, whether there should be more than one session a week, whether I should put in place a structure and then basically that's what we follow rather than this tutorials type of situation. It would become more lesson-like. I'm not really sure the best way of going about it. So if you've got any thoughts on that, just drop me a message, give me some thoughts on that, and I'll have a think. I've only got a few weeks to get it sorted, really. Okay, we'll call that an end. I'll hit the end stream button. Thank you very much for coming along. Really hope it's been useful. I've enjoyed today because it's Newton's Laws. I love them. Do look up Newton's Laws Blues online on YouTube. You should be able to find it. It's my little song. And have a good week. Stay safe. And don't go out even if you're told you're allowed to, because we don't want the infection rate to increase. I'm going to stop rambling. Have a lovely weekend.